Okay, the next lesson in this rather different approach to chemistry than, or even science as to what you've ever taken before, deals with, again, the graph that we were looking at for first order reactions, and a significant aspect of it, which is what we call the half-life, which is the time it takes for half the material to disappear or decompose, however you want to talk about it. We have, to remind you here, this is the graph that I'm talking about. So when you look at this script, this is the graph that I put on the script. We've had this before. You can just bring that straight up from the previous time that this graph was looked at for the first order reactions. But what's important about this is, this is a little clumsy here, so we're going to try and clean it up a bit for you. But you start off with a full amount of reactant. Whichever reactant you look at, it's really not important what that reactant is. So we use the hypothetical X. And then we come down here, and this, if you take a look at the distance from 0 to X, this would be the halfway point or the midpoint, which we call 1/2 X, or in terms of concentration, it's the concentration of X at T sub 1/2, which means concentration X when the half-life has been met. And because of the fact that this is not a linear relationship, it is a logarithmic relationship, this will never be a straight line. And because of that, you're technically never really going to have a complete point where all the material is gone unless you can reach close to infinity or some point in which two distinct molecules of the same kind can fight through a sea of products that have been created to eventually collide with itself, which will take a very, very long time. So from here to here, that time takes, which they call T sub 1, is the first half-life. That is the half-life, and this is the first half-life that this takes. And what that is saying is this. Yes, it takes X amount of time to go from here to here, but it's not going to take the same amount of time to go from here to here. As you can see, because if it was a linear relationship, that would be true. But because it's a logarithmic or curved relationship, the half-life is going to refer to the half-life from the starting point of which that half-life begins. And what I mean by that is this. If you start here, and you look to here, that's half the amount here. You start here, this is your starting point instead of up here, then half of this half becomes a quarter. And so the amount of time it took to go from here to here is the amount of time it took to go from here to here, and that time span is exactly the same as the amount of time it took for the first half to disappear. So half of the half is going to be the second half-life. And then if they were to do a third one, which would be right here, this would go across until the curve were to extend, and that time frame, which is from here to here, will go to right about here. And it'll keep going on and on, less and less and less and less, and it's what we call asymptotic to this x-axis, where it approaches it but never really intersects it. And we can mathematically determine these values by using the equation that we talked about for first order reactions. So, down here, so that can help. All right, so what we have here is this. We talked how the y-axis are those concentrations, or the quantity of X that we talked about there. And this is the designated T sub 1/2 is what we describe as the half-life. Okay, and we're going to be showing examples of how this is going to work. Okay, and remember I said on this particular screen here that this is not really X. They're implying that these two X are the same. This really should be written as 1/4 X. Okay, so we come back to this. And so we use T sub 1/2 for the first half-life and T sub 2 for the second half-life on that graph. But it's really T sub 1/2 1 and T sub 1/2 2 is a better way of describing it. So it keeps, the amount of time stays the same, but the value of the concentration gets less and less and less by half from the previous point. So what this means is that the first half will be 50% of the original material. The second half-life will leave 25%, which is 50% divided by 2, or 100% divided by 2 to the second power. So let's take a look at the mathematics of this. The original quantity is fully 100% of that matter. Now, we can use the concentration here, but we're going to look at percents, and then we'll show concentrations in just a bit. So this is at T sub 0, meaning the very beginning point as the reaction is about to begin. After it has gone a full half-life span, by definition, that means 50% remains. And that's going to be at T 1/2. Now, 50% is 100% divided by 2, and this is the first, so I'm going to do this right here and put a sub 1 here to show that's the first half-life. So this 1 here is the number of half-lives that this reaction has gone through at that particular moment in time. So we'll say 1 equals n. So we say 100% divided by 2 to the n power becomes 100% divided by 2 to the first power, which is at 50%. And this is kind of how we're going to look at this here. Okay? So we go back to that graph, and we see that this point right here is going to be half of the 1/4 x, and 1/2 of 1/4, well, you multiply 2 times 4 the denominator, you get 1/8 x. And so you go across until that hits, we said somewhere right around here, like that comes down. And, well, if this is 50% remaining, and this is 25% remaining, then half of 25% will be 12.5% right there. So, the next one, the next half-life span is going to be 100% divided by 2 to the second power. That's that 1/4 x that was not labeled very well on that graph. And so that's going to be 100% divided by 2 to the second power, and that's going to be 25%. So this is the second half-life sub 2. That's our n. That's what we're plugging in there, that 2. And then that next one that I just showed you is going to be at, we'll show you this is going on here, at T sub 1/2 sub 3, the third one. Then this is going to be 100% divided by 2, and n now is 3, and that will give it, if you type that out in the calculator just like that, you will indeed get 12.5%. Now, if you divide by 2 in your head, you don't have to go through this. You can see how this is going to go. The next is going to be 6.25% for T half sub 4, and then 3.125% for T 1/2 sub 5, and on and on and on like that. Okay? So that's how we can calculate using half-lives.